Okay, this is part 2 of our resistor circuit analysis, so if you haven't watched part 1, I would encourage you to stop this video and go watch that one. What we found out so far is that we have a current, and I should point out I've left off the omegas here on my resistors just in the interest of space. I would not encourage you to do that, but I'm writing on an iPad with my finger, and it gets a little hard to get everything in neatly, so I'm going to leave those off for now. What we found so far is that the current that's flowing through my 8 ohm resistor, I'm going to call that I1 is equal to 3 amps. And the current that's flowing through my 4 ohm resistor, I'll call that I2 is equal to 3 amps. And then what we said is that the current that flows across my loop will split, right? I'll have current that'll go in the upper loop, current that'll go in the lower loop, but then it comes back together on the other side, and I have a current that flows out. And what I've said is because that current has split, but it's recombined, then that current that flows into the loop and out of the loop also has to be 3 amps. But that doesn't tell me how much current flows through the 6 ohm resistor, how much current flows through the 3 ohm resistor. So we're going to figure that out now. Now, before we do that, let's use our brains and think about it. 6 is greater than 3, right? So what that says is that in the upper part of this loop, there's greater resistance than there is in the lower part of the loop. That is, it's easier to flow through the 3 ohm resistor than it is the 6 ohm resistor, right? There's less resistance, quite literally. So we'll expect to find that the current flowing through the 3 ohm resistor is greater than the current flowing through the 6 ohm resistor, just because it's easier. Current, like most physicists, is inherently lazy. We want to take the path of least resistance, quite literally in this case. Whatever has less resistance is where more current will be found. So that's what we would expect, right? So we've got to characterize it, then we're going to do some math and see if what we come up with matches what we know should happen. Alright, so my first step to doing this is to calculate the voltage drops across each of these resistors and then across the loop. Remember, I would encourage you to think about voltage drops like you're moving downhill. The positive terminal of the battery over here is the top of your hill, and the negative terminal of the battery is the bottom of your hill. And you're moving downhill as you go around the circuit. So as you go across the 8 ohm resistor, you drop a little bit. You've moved down the hill. And then as you go across the 4 ohm resistor, you've moved down the hill. And then as you move across the loop, you moved downhill a little bit. And at that point, right, you've got nowhere else to go. You're at the bottom of the circuit. You're at the bottom of the hill. So we know that the total voltage drops, if I add up the voltage drop across the 8 ohm resistor, the 4 ohm resistor, and across the loop, it's got to be 42 volts. That's only as high as my hill can go, right? If you're on the top of a hill, and if it's a 30-foot hill and you roll down and you travel 40 feet down, you would think that was strange, right? That means you've gone through the ground. Or if you only traveled 20 feet down, that means you haven't gotten to the bottom of your hill yet. So our hill is only 42 volts tall. So that's what our total voltage drops will be. So let's calculate that, right? I have everything I need to know to calculate that. Let's go across the 8 ohm resistor. V drop across the 8 ohm resistor. It's a lot of subscripts. That's okay. I can calculate this again using Ohm's law, right? V is equal to IR. I know what the current through that is. It's going to be I1. And my resistance, R1, I know what that is. It's just 8 ohms. So if I just plug in those numbers, I've got 3 amps times 8 ohms. I get 24 volts. So my voltage drop across the 8 ohm resistor is 24 volts. That's how far down the hill I've gone. Okay? It's a little bit more than halfway. 21 volts is halfway, which I do expect because that's the largest resistor, right? That's the largest resistance I have to go through. It means it's my largest drop, or my largest voltage drop. In the hill analogy, I've moved farther down the hill than I will in all the other ones. Okay, well let's do the 4 ohm. I can think I have space for that. V drop in the 4 ohm resistor is just IR. This is going to be I2 R2, which is just 3 amps. Sorry, equals 3 amps. R2 is 4 ohms. We know what that is. Well, I've got 12 volts. Right? So my voltage drop across my 8 ohm is 24. My voltage drop across my 4 ohm is 12. Right? So let's go to my next page. Let's go to a clean sheet. Let me add up the voltage drops I've gotten so far. 24 volts, that's terrible for. 24 volts plus 12 volts is equal to 36 volts, right? So I only have 42 volts available. That's as high as my hill was. So I think I can do the math here pretty easily to figure out what the voltage drop across that loop is. Now I could go to one of my equivalent circuits. Remember, I found that the equivalent resistance of that loop was 2 ohms. And I could do it that way, and you can. Well, in fact, let's do it that way to make sure everything lines up. The voltage drop, or the equivalent resistance of that loop was 2 ohms. So let's do that, and we know that the whole current flowing through that loop is 3 amps. So my voltage drop across that loop is equal to 3 amps times 2 ohms, which is equal to 6 volts. Right. I could also do it this way. 42 volts minus 36 volts, right? 36 is what I've gone through so far. 42 is my total available. Surprise, surprise, that equals 6 volts. So either way works, right? You can calculate it using the equivalent resistance. You can calculate it using some simple arithmetic. If you trust your math up to this point, use the arithmetic. If you don't, use the equivalent resistance. It's 6 one way, half a dozen the other. Okay, so at any rate, I've got that. Now let me go to another sheet and redraw this loop. So I have I believe a 6 ohm resistor up there and a 3 ohm resistor there. So this is my 3 ohms, this is my 6 ohms, and I know what's coming in here is 3 amps, and I know what's going out is 3 amps. I also know now what the voltage across this loop is. It's 6 volts. And this is a parallel configuration, so I know that both resistors see, quote unquote, the 6 volts. This is the voltage drop across both, this is the voltage connected to both resistors, right? So now I can calculate the current. Remember, I've said that this, I believe, is I2. Nope, that's I3. This is I4. That's how I've called them in previous videos. So for I3, I've got V across the 6 ohm resistor, or V to which the 6 ohm resistor is subjected, is I3R3, where R3 is the 6 ohms. What I'm interested in is the current flowing across that, right? So I just solved this for the current. I3 is equal to V over R3, which is equal to 6 volts over 6 ohms, which is 1 amp. Yay! Alright, so now I know what current is flowing through the 6 ohm resistor. To find the current through the 3 ohm resistor, again, I have 2 options. I can form the same equation, V, which again is going to be 6 volts, is equal to I4, R4, which is I4 is unknown and R4 is the 3 ohm resistor. I can solve it for the current just like I did here, and I can get an answer. Or I can, again, use simple math because I know that the total current has to be 3 amps. And I found that 1 amp is flowing up here. Let me change colors. 1 amp is flowing here, right? So if 1 amp is flowing up there and the total is 3 amps, then it's got to be 2 amps here. And if you form Ohm's law again using that resistor, you will find that it is 2 amps. So I've got 2 amps going here, 1 amp going here. And that's exactly what I expected. Remember the discussion. 3 ohms are less than 6 ohms. The resistance of the bottom leg is less than the resistance of the top leg. So I should expect to find more current flowing in the bottom leg than I do the top. It's easier for it to do so, and I do. And please notice that the current that I found is inversely proportional. If I form the ratio of these resistors, I get 1/2 of 3 ohms over the 6 ohms, which is the inverse of the ratio of the currents flowing through them. Of course, you can show that mathematically, but that's not an accident, right? The amount of resistance determines the amount of currents in a very mathematical, proportional way. Alright, so that's all we can do as far as the currents. We can talk about the power dissipated by each of these resistors, which I will do in the next video, part 3.